Hello and welcome to Honors Function. After studying the graph of sine and cosine, let's now turn our attention to the graph of secant, cosecant, tangent and cotangent. Before we looked at the graph, let's study the property of these functions. Namely, I will look at the domain, the range, and the parity and periodicity of these four functions. Let's begin. So the sine and cosine we justified were defined over the set of all real number. It is not going to be the same for these four functions because if you look at them, they all have a denominator with a variable at the denominator. Therefore, when this variable is equal to 0, there will be a problem. Okay? So I will group together secant and secant and tangent and cosecant and cotangent because these two functions, secant and tangent, have the same denominator cosine. Cosecant and cotangent have the same denominator sine. So the domain of secant and the domain of tangent are the same, and it's made of all the x's such that cosine x is not equal to 0. Okay, so let's look at it graphically. You will see it's very easy to understand. So what's going on graphically? Here's the x-axis, y-axis, y equals 1, y equals negative 1, pi over 2, pi, 3 pi over 2, 2 pi, and then same on the other side right here. So how does cosine go? Well, cosine starts at the max, cosine x, then it's 0, negative 1 at pi, 0 at 3 pi over 2, 1 at 2 pi, 0 at negative pi over 2. Here we go. This is a few branches of sine right here, a few arcs of sine. So where's cosine x equal to 0? Well, we can see graphically at pi over 2, and therefore tangent and secant will not be defined at pi over 2. They will not be defined at 3 pi over 2 because cosine is equal to 0. They will not be defined at negative pi over 2 and negative 3 pi over 2. And of course it goes on and on and on, okay? So graphically, I can see where secant and tangent will not be defined, or where there will be defined. And we could do the same with cosecant and cotangent, okay? The domain of cosecant is going to be the same as the domain of cotangent, and this is made of all the x's such that the sine of x is not equal to 0. So in this case, I will want to look at the sine graph right here, pi over 2 pi, 3 pi over 2, 2 pi, negative pi over 2, negative pi, negative 3 pi over 2. So how does the sine goes? Sine 0 is 0, 1 at pi over 2, 0 at pi. Here we go. Here's one period of sine, and in the other direction, here's another period of sine right there. I'm going quickly. My graphs are not very good, as you can see. So where is sine equal to 0? Well, wherever it hits the x-axis. So we have right there on the y-axis sine is 0. Right here, sine is 0 at pi, at 2 pi, at negative pi, and on and on and on. So again, visually, I have no problem finding out where sine or cosine are equal to 0. Let's do it now analytically. So you want to solve the equation cosine x equal to 0 with x in R, right? We want to figure out all the value where cosine x is 0. So what's going on? Let's take the unit circle right here, and we know that cosine of x right here, x is this arc length, but it's also this angle right here, and the cosine is the x coordinate of the point on C1 right here. That's C1, right? So where's cosine equal to 0? When the x coordinate is 0. So on C1 I have 2 points. I have this one right here, and I have this one where cosine is 0. What's this point? This is pi over 2, but it's also 5 pi over 2 and 9 pi over 2. So, or it's also negative 3 pi over 2. So it's 5 pi over 2 plus k times 2 pi, right? 2 pi is a full revolution. I can turn 2 pi and I will be back on pi over 2. What's this angle? Well, it's negative pi over 2. I can also call it 3 pi over 2, right? But it doesn't tell me to take an angle between 0 to pi, so this is fine. Plus k times 2 pi, right? Well, there is a nice compact notation that describes both these notation together, this position, and the notation is going to be pi over 2, so you go right here, but instead of turning by a multiple of 2 pi, just add or subtract a pi right here, all right? Pi is just this right there. So 1 pi, 2 pi, I'll be right there, minus 1 pi, I'll be right here, right? So this is where cosine is equal to 0. Let's write that down. Cosine x equal to 0 if and only if x equals pi over 2 plus k times pi such that k is an integer, okay? This notation describes all the position where cosine is equal to 0. And you can see right here on this graph, this is for k equals 1, right? I'm sorry, this is for k equals 0, pi over 2 plus k pi. So k equals 0, you're right there. This is for k equals 1. This is for k equals negative 1, k equals negative 2, and on and on and on, okay? All right, let's do the same for sine now. How do we solve analytically sine x equal to 0? So sine x equal to 0 with x in R, right? Okay, so how do we solve that? Well, here we go again. Here's C1. Here's the x and the y-axis. Let's take an angle x. Let's take a real number x that is actually an angle right here. And x is right there. Okay, what is the sine of x? Well, sine of x is the y-coordinate of the point. This is sine of x. Where is the y-coordinate equal to 0? So when the point on C1 is right here, or right there, right here, right? How do you describe this position? Well, this position is 0 plus 2k pi, okay? While this position is pi plus 2k pi. Okay, k pi times 2, it's kind of 2k pi here. Let's write 2k pi here. As we did above, we can find a compact notation that describes both of these positions together. And the compact notation is going to be k pi, okay, with k being an integer. If k is 0, you're right here. If k is plus 1, you're there. Plus 2, you're here. Minus 1, you're there. Minus 2, you're here, right? So basically all the evens will be here and all the odds will be there, all right? And this is a solution of the equation sine x equal to 0 if and only if x equals k pi with k in z. That's it, okay? Now that we know that we know the domain of these four trigonometric function, right? This is all x's except pi over 2 plus k pi with k and z, same with that, while these are all the x's except pi plus k pi with k and z. Now, what happens graphically at pi over 2 for secant and tangent and at pi plus k pi for for cosecant and cotangent? I guess we don't need this pi right there. Okay, what happens graphically? Okay, so for that, let's go back to our representation of, let's take, for example, tangent. I'm going to show you on maybe, let me see, maybe we can do them all. So here's C1, here's a y-axis, right here. Here's the axis of 10, right here. Here's the axis of 10. So let's take a few x's right here. Here's one x, here's another one, and let's make our x's move towards pi over 2, right? I'm moving towards pi over 2 right here, and then right there, and then I guess I need a little bit more room at the top, but it's pointless. It would go very far off right there, okay? So x is moving towards pi over 2. Let's check out what happens to the tangent of x. Where's tangent? This is x right there. Where's tangent x? It's represented by this segment right here. Here's the first one. here's the second, here's the third, and then the fourth, and you can see right here, they're getting larger and larger and larger. And if you are really getting close to pi over 2, the value of 10 or secant, where's secant right here? Secant is this one right there, and then this one, and then this one, and then this one, right? That's secant, right? And these value, these segments are getting longer and longer and longer. So basically, as x approaches pi over 2, what do we notice about 10x and secant x? They both approaches infinity, right? They're getting larger and larger and larger and larger, and they approach infinity. And you can understand why in the other direction, right here, if x approaches negative pi over 2, then you're going in this direction for 10. So 10 as x approaches negative pi over 2, 10x approaches infinity, while secant x, now this is your, oh sorry, I'm not turning this way, I'm going towards negative pi over 2, so I'm turning the other way, I'm turning this way right here, I'm turning this way, so this is the terminal side of the axis, right? That's the terminal side of the axis, and so secant x is gonna be positive, right? On the terminal side right there, secant x is positive, right? And so secant x, on the other hand, still approaches, sorry, I should have been a minus infinity right here, and secant x approaches plus infinity. 10x goes down because that's a positive side of your 10 axis right here. Okay, this is a positive side of the 10 axis, but the positive side of the secant axis is the terminal side of the angle, okay? And the terminal side is right there. All right, so a little difference at negative pi over 2. Let's go over a few examples right now. All right, let me do the first example. Find the domain of the function. All right, so this is a cosecant x. So we do not want what's inside to be equal to k pi, okay? Because the cosecant of anything like k pi with k in z is not defined. So the domain is made of all the x's such that pi over 2 x plus pi is not equal to k times pi. That's it. Solve this for x and you'll have the domain. So let's divide by pi everything right here. So we have a 1 right here, right? Okay, so what does that mean? That means x over 2 plus 1 is not equal to k being an integer, right? So what does that mean now? That means that x over 2 is not equal to 1 plus k. Now, 1 plus k with k in z, well, that's the same as k, okay? I mean, it's another k, right? Because it's 1 plus k, so it's not the same k. But it's an integer because k is an integer, so 1 plus k is going to be an integer. So, what do we have? We have x different than 2 times, here, I'll write 1 plus k if you want to, but we are going to simplify that. 2 times k plus 1 with k in z. So, what are you describing here with this notation? 2 times k plus 1 with k in z. Well, you're just describing an even number. That's all. This is an even number, right? So, x is not an even number, so let's write that 2p such that p is in z. That's it. X cannot be even. So this function is defined everywhere except on the even number. Okay? I'll let you do example 2 and 3. Let me move on to the range of this function. So let's talk about the range. For that, I need the graphical representation of sine and of tangent and cotangent. So if you take an x, either positive, so let's if you take a small x right here, this is the 10 of x, and then you make it bigger, that's a 10 of x right there, and then bigger right here, and you can see 10 of x is getting larger and larger and larger, and it goes up to infinity, right? Positive infinity. And of course, if x is negative right there in the other direction, same with 10x. So just with these x's right there between negative pi over 2 and pi over 2, 10x goes in both directions towards negative infinity and towards plus infinity. It would be the same with cosine, with cotangent. Check out this cotangent right there. This is a very large cotangent. It could be even larger right there, right? That's cotangent right here, right? And then they're getting smaller, closer to 0 right here. That's cotangent right here, closer to 0. And then going negatively, you have here a cotangent, here's another one, right? The length of this segment is getting larger and larger and larger, okay? So the range of tan and the range of cotan are the same, and these ranges are all real number, okay? And we saw it with the visual representation of tan and cotan as length of segment. Let's talk about secant and cosecant right now. We could do the same actually. I can do the same for secant and cosecant. I can do it algebraically, or I can do it, I can do it graphically, or I can do it analytically. Let me choose to do it graphically. Very, very simple. Check it out. To find the, I'm going to do it for secant, right? To find the axis of secant, you do this, right? So you take a small angle x right here, and then another one right there, another one, another one, another one. Okay, where's the, and then let's take some negative x's too, okay? So I'm moving either in this direction or in this one right here. Where's the secant of x? Well, right here it would be there, and then it's getting bigger and bigger and bigger, longer and longer and longer, and we said the length is going to go to infinity, okay? That's why you have an asymptote. Same thing here. The length is going to go to positive infinity, okay? Don't forget the positive side of the secant axis, and that's why you have another asymptote right there. Now, what's going on around 0? Well, here's secant. Oops, sorry, that's too far off right here. It stops at the intersection with the tan axis right there, and then here, and then here. So what's the lowest value for secant? Well, it's right there. That's 1, right? 1 is the lowest value. And after that, you're outside the circle. Check it out, right? Because the circle goes like, I'm going to zoom in a little bit. The circle goes like this, right? Here's your tan axis, right? And so secant, when the angle is 0, comes right there. And so it's 1. And after, when it passes 0, then it's no longer 1. It's bigger than 1, because 1 is a radius of your unit circle. This right here is 1. This is 1. This is 1. And you see that secant is a bit longer than 1. Okay, so the lowest value for secant is 1, and it can be bigger than 1. Now, if you take secant on the other side, suppose you take an angle right here, right? So secant now would be on this side, but it would be negative, right? That would be the length of secant. And so what's the value for secant? It would be the range of secant. All right, so let's see. The range of secant goes into negative infinity, -1, that's the highest negative value, or 1 infinity, and that's the lowest positive value. And it will be the same for cosecant, okay? Cosecant goes between negative infinity and -1, or between 1 and infinity. We could have checked that analytically. There's a very simple property that tells you if a number is between 0 and 1, then the reciprocal of that number is above 1. Okay, 1 over cosine x has to be above 1, and the same thing is true on the negative side. If a number is between 0 and -1, then the reciprocal of that number, 1 over cosine x, is below -1. Okay, and because that's the range of cosine, then that would be the range of secant. Let's go over some examples. All right, what's the range? Example number 4, what's the range of this function right here? So I know this will not affect the range, that affects the domain. So let's focus on the 3 different graph shifting that affects the domain. The range, sorry. So what do you start with? You start with negative infinity, -1, union 1, infinity, right? Now you need to remember graph transformation. First thing that happens is a vertical dilation. You multiply by 3. So that's negative infinity, -3, union 3, infinity. Okay. The next thing that happened is a reflection through the x-axis. But in this case, because your range is so symmetrical, right? It's completely symmetrical. It's not gonna show, right? So you're gonna be gone from this set and you're gonna go into this set right here. It looks like it's the same, but there was a shift, right? Let me remind you actually what would happen. Normally, this shift right here with a negative sign will take an AB. Here, let's put a parenthesis right here, and it will turn it into a negative B, negative A. Right? That's what you do. But because of the symmetry right here, you don't see it. And finally, what's the last move? 2 up. So let's bring it 2 up. Negative infinity, negative 1, union 5, infinity. That's it. Okay? Let's quickly go over parity and periodicity, and let's check out the graph of these 4 functions. So we know that cosine is even, and we know that sine is odd. Okay? Therefore, secant is also even, and cosecant is odd. I'll let you check that. And actually, if you multiply or divide an even function by an odd function, you're going to get an odd function. So we also have that tan is odd and cotan is odd. Okay? So even is only cosine and secant. Let's talk about the periodicity now. So the periodicity of cosine and sine is 2 pi. Therefore, the periodicity of secant is also going to be 2 pi, right? Check it out. What is secant of x plus 2 pi? It is 1 over the cosine of x plus 2 pi, but that's the same as 1 over cosine x, which is equal to 1 over secant x. Oops, sorry, which is equal to secant x, which is equal to secant x, right? So secant and cosecant have a period of 2 pi. You may think it's the same for tangent. And it's surely true that if you look at the tan of x plus 2 pi, it's going to be equal to the sine of x plus 2 pi over the cosine of x plus 2 pi. And this is the same as sine x over cosine x, which is tan x. So it is true that the tan of x plus 2 pi is tan x, but 2 pi is not the smallest number that will make that true. There is a smaller one. Let me show you. Let's now check out the tan of x plus pi. What is that? This is a sine of x plus pi over the cosine of x plus pi. Now, the sine of x plus pi is not equal to sine x. Let's check it out. Right? Here we go. Let me take a small angle x right here, x right here. So this is sine x, and this is cosine x. And let's look at x plus pi. Where's x plus pi? X plus pi is going to be right here, right? X right here plus pi right here. X plus pi. So where's the cosine of x plus pi? It's right here. This is a cosine of x plus pi. And this is the sine of x plus pi. Now, it would be very easy to show in geometry that this triangle is actually congruent to this triangle right here. Okay, the angles are the same right here. This angle and this angles are the same, so these triangles are congruent. Therefore, this side is congruent to this side, and this side is congruent to this side. They just have different sign. So what does that mean? That means that the sine of x plus pi is actually equal to the opposite of sine x, while the cosine of x plus pi is actually equal to the opposite of cosine x. So what is this? This is sine x over cosine x. That's just tan x. And you see, the period of tan is just pi. That's it. That's all. Alright, time to look at the graphs. Let's check out the graph quickly. I'm going to try to be done very quickly, but this video is a little bit on the long side. Well, I just introduced 4 graphs. The next one will be shorter, I think. Alright, I propose we only look at secant and not at cosecant. The construction is exactly the same. And the way I graph a secant is very simple. I will graph the cosine first, which is not the important graph. I can erase it after, right? So let me graph the cosine right here. Here's cosine right there. Again, I'm dashing it because it is not the important graph, right? I want to graph secant. You will understand why I'm graphing cosine. Here we go. Here's my cosine graph. Okay, now what's going on? Well, every time cosine is equal to 0, secant is not defined. And we know we're going to have a vertical asymptote right here, vertical asymptote right here, right here. Okay, power 2, 3 power 2, 5 power 2. Where's negative power 2? Right here. Cosine is equal to 0, and cosine is equal to 0 right here. Okay, now, when cosine is equal to 1, what's 1 over 1? That's 1, so secant is 1 right here. When cosine is negative 1, secant is negative 1, right? So the local max and mean for cosine are going to be local max and mean, or local mean and max for secant right here. And then what's going on? Well, then secant grows larger and it has an asymptote. So here we go. Here we go. That's the asymptote of secant right there. And another one right here. And another branch right here. Here's your secant graph. So it's a series of branches like that. Like that. And an infinite series of branches like this, okay? Here we go. This is secant, okay? Now be careful, guy. What we call a period of secant is this right here. That's 2 pi, right? A period is 2 pi. You need 2 bridges, one up, one down to get a full period. Let's check out the graph of 10, shall we? So for 10, we have the same vertical asymptote, right? Which is at pi over 2, 3 pi over 2. It's power 2 plus k pi, right? Negative power 2, like that. Okay, now, what's going on for 10? Well, there's another point that I kind of like. I'm rushing a little bit out of time here, but I still want to show you this point. Pi over 4. When you divide this right here, folks, between negative power 2 and power 2, that's a full period for 10, right? This is a period. This is t equals 1 period of 10, right? And I kind of like 1/4 of a period, because what's a 10 of power 4? Well, it is 1, right? And here's negative 1 right there. The 10 of power 4 is 1, and the 10 of negative power 4 is negative 1. This is what's going to indicate a vertical stretch for 10, okay? Stretch or shrink for 10. Then 10, 0 is 0, and then we have a vertical asymptote. We saw it graphically. Here's 10 right here. And this is 1 full period of 10. Therefore, you're going to repeat this branch right there, okay? Here is 10. Guys, I'm really running out of time. But basically, cot10, I'm explaining in my notes. First of all, the asymptote would be on the y-axis and at pi right here, okay? That would be my asymptote for cot10 right there, okay? And the graph, well, the graph would go the other way. It would go like this, okay? So while 10 is increasing, cot10 is decreasing, but it's the same type of behavior, okay? All right, thank you for watching this very long video.